Over the past few lectures, we've been looking at the issue of evaluation. And in particular, we've been describing the process of evaluation in terms of our language for describing processes, namely scheme. This has allowed us to explore variations in how we build evaluators, but it's left us with the slightly puzzling idea that we're describing scheme evaluation in scheme itself. And while this has a wonderful meta-circularity to it, it isn't as convenient to think about things in terms of such high-level abstractions. Beginning in this lecture, we're going to turn around and go the other direction. That is, rather than building up abstractions in terms of describing evaluation, we're going to go down into the details of the machine and build a CPU, a central processing unit. We're going to design a CPU simply assuming that we have available some wires, some logic, little networks of gates if you like, some registers to hold values, and a sequencer that controls how information is moved around within these registers. We could, of course, design machines to do lots of computations. We could design a little processor to compute factorial or Fibonacci or some other particular function. But, of course, that's not nearly as convenient as designing a little processor that will, in fact, compute anything in a language. So our goal is to build, or design at least, a little CPU that will interpret scheme as its machine language. And what we're going to see is that we can do this in stages, starting with just building basic iterative algorithms in hardware, then adding in recursive algorithms, and then showing how we can, in fact, implement all of scheme in hardware itself. To set the stage for the journey we're about to embark on, let's think about what I'd really like to have in terms of computation. Let's assume that I have a little machine that computes greatest common divisor, a GCD machine. It's built out of some wires and registers and logic somehow. And in fact, shortly we're going to build such a GCD machine out of some simple pieces, so it's going to be something we can do. Nonetheless, assume we have such a machine available. This means I can pass some signals into the input wires, representing input values, numbers if you like, and a signal will come out the output wire representing the number that's the answer we get when we compute the GCD of these two input numbers. And of course, if I've done that right, that will hold for any input I put in. Any input into this GCD machine will give me a new output corresponding to that computation. Now, I don't really want to build a new machine for everything I'm going to compute. That's far too much work. So here's what I'd really like. I'd like to be able to take a description of that GCD machine, a circuit diagram that tells me exactly what registers and wires and logic to use. And I'd like to be able to pass that description, that circuit diagram, off to another machine, sort of the ultimate machine. And here's what I want that ultimate machine to do. I want it to reconfigure itself, rechange the wiring, the connections, the registers, the logic, so that it now looks like GCD. It behaves like GCD. I'd like that ultimate machine, in fact, to do that for any circuit diagram. I give it a circuit diagram, it reconfigures itself. So if I happen to give it the circuit diagram for GCD, it reconfigures itself to look like GCD, and then, given inputs that are inputs to GCD, it will behave like GCD, do the right computation, and give me out the correct answer. And it'll do it for any description of any diagram that I want. Now, how would I design that ultimate machine? How would I build a machine out of registers and logic and wires that would have that property? That seems kind of tough. And it may be doable, but it doesn't seem obvious how you'd go about doing it. So let's step back and rethink. We said we had a description of GCD. We described it as a circuit diagram. But there's another way we could describe GCD. For example, we could describe GCD in our normal way of describing processes, as a procedure. And we'll do that in a second as well. But imagine we have done that. Now let's think about passing that procedure description into a machine we're going to call a universal machine. And it has the property that it takes that description, reads it in, and then reconfigures itself so that it simulates or emulates the process described by GCD. Meaning if I give it any inputs, I'll get the right output for that described procedure. Now the question is, could we build that machine? And while it looks a lot like the previous thing we had on the left side of this slide, in fact, we know how to build that machine. That's called a val. That's exactly what a val is. It's a description of a universal machine. It says, give me any legal description of a process, and I will emulate that process, taking in inputs and handing out outputs appropriately. So in fact, our goal then is to decide how to build that universal machine, how to build a val in register machines, how to build a val out of much simpler pieces of hardware. And if we can do that, then we have this property that we can do anything. And in fact, we don't need to build special purpose hardware for other things, because a val, that universal machine, will do everything we need. This idea of a universal machine is a central component of computer science. As we saw in an earlier lecture, this fundamental definition of computation in terms of universal machines is based on an insight due to Alan Turing. Turing was addressing Hilbert's famous decision problem, which asked whether all of mathematics was decidable. That meant could one devise a specific method that could take any assertion about mathematics and determine if it were true? To answer this question, Turing created a definition of a machine, now called a Turing machine, that led to the generally widely accepted Church-Turing thesis. Any procedure that could be reasonably be considered to be an effective procedure can be carried out by a universal machine, and thus by any universal machine. Thus, all we have to do is build one machine out of hardware, as long as we can make that machine a universal machine. For example, if we make it an evaluator. If we can do that, then that machine, that evaluator, can execute the computation for any other process that we can describe in legally, and thus includes any other evaluator. So let's start working our way towards building that universal machine out of much simpler pieces, building that evaluator from registers and logic and wires. To do this, we're going to look at some simpler processes first and work our way up. And in particular, let's go back, in fact, to GCD. Here's a description of the process of GCD. We happen to be describing GCD in the language that we've been using, namely scheme. But here's what it says. It says to compute the greatest common divisor of two numbers a and b, do the following. If b is 0, then we're done. The answer is just a. Otherwise, the GCD of a and b is the same as the GCD of b, and the remainder we get by dividing a by b. And so we have a little description of that process in terms of scheme. We also have a description here in terms of English. Let's see how we can actually build a machine out of very simple pieces that would do this computation. Well, here's a top-level view of how we're going to build that machine. We're going to need some pieces. And in particular, we're going to need some pieces to store numbers. We'll call those registers. They're shown here in the square boxes. A, B, and T are all different registers. Think of those registers as being large enough to hold some representation in electronic form of a number. Of course, we'll need some way of moving information from one register to another. We'll have to have some way of getting values from one register into a different one. So we've got wires that connect those up. And we've drawn a little circle with a cross in it to indicate that there's a way of controlling the movement along those wires. Little buttons that we'll be able to push to say when we want information to flow from one register to another. Besides registers and wires, we'll also have, or assume we'll have available to us, some simple logic. Little units that we've gone and bought from a supplier somewhere. And in this case, we've assumed that we have one simple little piece of equipment, one little circuit, called remainder, which is shown in that trapezoidal-shaped box. And it has two wires coming in and one wire going out, saying it's taking two inputs and giving us one output. And finally, we'll need to have ways of testing things, checking to see whether, in fact, a value has a particular form or not. So we've got little tests shown in circles, like the equal tester up there, a little piece of circuitry, and it has a constant value, in this case a 0, shown in the triangle that's passed into it. And there are the pieces of our little circuit diagram. In fact, what we've drawn here, as we'll see shortly, is a data path, a set of connections between the components of our little register machine that are going to let us move data around in particular order. In addition to our data paths, that is our little diagram that has wires and registers and components and circuits all glued together, we need a way of deciding how to move information around in that little system. We have to have an ordering or a controller that sequences how information is moved from one register to another. For that, we'll have a set of instructions. And we're going to come back to this, but the idea is to have a simple set of instructions that actually describe in what order to move things around. For our purposes, these instructions will look a lot like scheme. In fact, they're set up that way so that we could build a simulator to simulate the circuits inside of a register machine. But this is not full scheme. As we'll see, these instructions have very particular forms, and they basically allow us to do things like decide whether a particular test is true or not, make a decision as to where to go based on that, and otherwise move information from one set of registers into another through the opening of one of those buttons on that previous diagram. We'll come back to the details of what these instructions mean in a second. And in fact, we'll connect the two pieces together in a very important way. Given that little circuit, given that data flow with all the registers and pieces in it, and given a sequence of instructions, we want to have the instructions control how things are actually moved around in the data paths. So we'll have another unit in our little complete register machine called a sequencer. It has inside of it a thing called a program counter. And that program counter basically just keeps track of which instruction, which line of the instructions we're currently dealing with. The sequencer will basically ask the instruction at that line to do its thing, and then in general increment the program counter by 1 and move on to the next instruction. As we'll see, most of the instructions will involve the equivalent of opening up one of those buttons in the little data flow diagram. That is, moving information from one register into another, or potentially through one of those little circuits, one of those operation boxes, and into another register. Occasionally, however, the instruction will involve a test, and when that happens, a sequence of things occurs. First of all, using the little circuit that does the tester will cause a single bit to be output, a true or false, if you like, kind of value. That output wire goes to a special register called a condition register, and that sets a value in that condition register. That condition register then is input to the sequencer, which looks at that bit and makes a decision. Depending on whether the bit is 1 or 0, the sequencer will either move on to the next instruction or will go to some other place in the sequencer by changing the program counter. Or said in other words, depending on what the value of that condition register is, the program counter may be incremented by 1, meaning go on to the next instruction, or in fact it may be set to some very different value which will cause us to jump to another place in that sequence of instructions. So there's what a register machine looks like. It's got a set of data paths connecting up registers, wires, little pieces of circuitry. It's got a sequence of instructions that decides how to move things around in that data path, and it interacts with a little sequencer that lets us control that actual movement of data. Now what we're going to do is take these ideas, look at them in more detail, and see how we can start building up machines, beginning with very simple things, but working our way towards building the universal machine. So let's look at what we have then. Here's a standard circuit diagram. As we'll see, it's the circuit diagram or the data path for, in fact, the GCD machine. And we have inside of there the following. We have registers, which are places that hold numbers. We have operations, little pieces of circuitry that define our primitive kinds of things. We have buttons that control movement from either operations or registers into other registers. We have wires, obviously, to do the movement. We've got places that hold a constant value for us. And we have tests, things that set a single bit on a condition register in order to help us decide where to go next. And the behavior of each of the components is fairly straightforward. A button, when pressed, causes the value on the input wire to flow through to the output. A register is a storage place that holds a number or a value, if you like, inside of it. But it has the property that it outputs that stored value continuously. It is constantly putting that value onto its output wire. It changes its value only when the button on the input wire is pressed. And once it has done that change, that new value is constantly output. One of our operations, one of our little pieces of circuitry, has the property that the output wire's value is always some function of the input wire's values. And that is also constantly output after some appropriate time delay. That is also constantly output on that output wire, the same way a register is constantly outputting some value. And the test, as we saw, is some operation that does some sort of computation, much like ordinary operations, with the difference that its output is a single bit, either true or false, which goes to this condition register, which is going to be used by the sequencer to decide whether or not to change the program counter in an unusual way. Let's start with a simple little example of how opening up these buttons on the wires moves information around inside of a little register machine. And in particular, let's look at how we could go about incrementing a register. So here's a little data path. I've got a single operation, add, that takes in 2 inputs and just adds their results out. And I'd like to know what sequence of button presses will result in the register sum containing the value 2. Note that initially we don't know what's inside of sum. It comes as a register, but there could be anything inside of there. So we've got to come up with a sequence of button presses that will move things around. Remember, the outputs of the wires from each of these boxes are continuously outputting whatever that constant value is. Well, clearly the first thing I need to do is set sum to be 0. Zero it out so that I can start from an initial point that I know about. So I'll open up the button X. That allows the value 0 coming from that constant to flow through the wire into the sum box, changing sum to be 0. And some small amount of time later, that will flow out of the sum box, which is just a register, into the output through the plus, taking in the 1, and that will mean that the value 1 will now be coming out of the plus box. Notice that that is going to simply keep coming out of the plus box along that wire until it hits the button Y. Now that value 1 is sitting in front of the Y button. I've got a 1 available, so what I could certainly do now is open up Y and push that into sum. That is, increment the sum register by 1. Thus the value 1 flows into the sum register, and as a consequence flows through the sum register onto the output wire, and therefore through the plus operation together with the constant 1, changing the output there to 2, which flows back around to the Y button. So we can repeat this again, pushing the Y button to let that value flow into sum. Sum changes its value, and that value flows out and through the plus box, and now the value 3 is coming out of the plus box and has gone around that wire and is sitting in front of the Y button. But at this stage we're done. We've come up with a sequence of button presses that gets the constant value 2 into the sum register. And the fact that there's a 3 coming out of the plus box doesn't matter. So in fact, we see that the sequence we want to use here is to press X followed by Y, causing sum to increment up until it gets to the value 2. So we can see that coming up with a sequence of button pushes can let us move information around in a little register machine like this, getting things from registers through operations and back into registers. So let's look at how we do GCD. Here again is the description of GCD, and from this we can figure out a few things. We'll need at least a register for A and a register for B, since we've got to hold those two values. We're going to need an equal tester and a constant 0, and we'll need a remainder box, and we'll assume that that's available to us. Let's turn to building a little register machine that would compute GCD based on this description. And this description, in some sense, tells us the order in which we ought to be pushing buttons to move things around. The straightforward way to build a data path for GCD is as follows. We know we're going to need two registers, A and B. We'll assume that initial values get loaded into them somehow. That's not crucial. And we'll need a little remainder box. And the idea is very simple. We'll take the value of A and B, we'll compute the remainder, and then we'll let that remainder be the new value for B, we'll let the value of B be the new value for A, and we'll keep doing this until we get down to the last place, when we're done. And of course we know we're done when the value of B is equal to 0, in which case the answer is sitting in A. And we haven't put the test box in there. We can imagine doing that. Notice that we've got a slight problem, though. And the problem is one of synchronization. Let's suppose I open up the button Y. That means the value coming out of remainder will go straight into B. Oops, but I wanted to get the value of B into A, and I've already clobbered that before I could do it. Okay, let's suppose I open up X first. I'll let B flow into A so I can safely move the remainder in there. Oops, by doing that, I've done that before I can actually get the remainder of A and B out of the remainder box, so again, I've messed things up. This suggests I need to add something that will temporarily hold a value while I can move things around. And notice in this case of simple register machines, we have to think about how to synchronize the movement of information, which we didn't have to do in higher level things like a val. So let's modify our diagram to put in a temporary register and another button so we can actually control when things come out of the remainder box into a register and when things go from that register either into B or into A. So now let's think about the order in which we want to open up the buttons, X, Y, and Z, in order to allow information to correctly flow through this data path in order to compute the GCD. Well, here's the sequence. Assuming we have some values loaded into A and B somehow, the first thing we want to do is get that remainder and save it away. So we open up Z to move the remainder down into T temporarily. Having held on to that, we now can go ahead and change the values of A and B, but we need to do them in the right order. We need to open up X to move the current value of B into A. Having done that, we can then safely move the new thing into B by opening up Y so that the remainder flows into there. Having done that, we can then go through exactly the same sequence again. We can compute the new remainder by opening up Z, let the new value of B flow into A because we've held on temporarily to what we need, and having cleared B, we can then open up Y to move the remainder into B. And at this stage, if we had our tester, we'd know that we're done and we can stop. Notice a couple of things here. One is that the order in which we actually do things now matters. We've got to make sure we clear one register before we clobber it with a new value. And the second thing to notice is that we have a loop, if you like, here. We're going through the same sequence of operations. Z, then X, then Y. Z, then X, then Y. And we keep doing that until our test actually held. We'll come back to that shortly. Now, we need to actually describe somehow that sequence of operations, that order of button pushes. And for that, we have a set of instructions. Here's the basic form of the instructions for GCD, and we want to talk through the kinds of things we can have in these instructions. As we noted earlier, while these look like scheme expressions, don't be fooled. They're simply set up that way so that we can write an evaluator for this register machine using the same kind of syntax. But in fact, the instructions in this little register machine have a very simple form. The first kind of instruction is an assign instruction, and notice its format. Assign takes the name of a register, and in some cases simply a designation for another register, such as open paren reg B. And what that is saying to do is to open up the button that moves the contents of register B into register A. Assign can also have a button that moves the contents through an operation box. So notice that the first assign statement here says, take the button and open it that causes the values of register A and register B to flow through the remainder box and into register T. Also notice that these instructions define, in some sense, the connections that have to be in place within the data flow path itself. Other instructions in our language deal with branching, ways of testing something, setting a condition register, and then going someplace within the instruction set. And those places to go to are simply created by putting labels inside of the instruction set. And we'll come back to that shortly. But here basically is the sequence of instructions we have, and let's talk about how we're going to use those to connect to the data paths. To connect our instructions to our data machine, we have a controller that generates a sequence of button presses, opens up the valves, if you like, on those wires. It consists of two parts, a sequencer and a set of instructions. Now, the sequencer is our way of actually activating the instructions. And inside of that sequencer, there's a special register called a program counter. It basically points to the location in memory that holds the next instruction, or if you like, has the line number of the next instruction. The operation of this sequencer is to basically activate each instruction in turn, using the program counter to say, where's the instruction, cause that instruction to be activated, which will generally open up a button and have some information flow through the machine, and then increment the program counter by 1, moving on to the next sequence. And it will keep doing that in order until it hits a particular kind of instruction. The instructions generally will just command a button press, that is, cause information to flow through some portion of the machine and into a new register, or in some cases, it will cause the program counter to change. We call these branch instructions, and we're going to see that we'll have several kinds of branches. These will generally involve either changing the program counter directly or setting up a test that puts a bit into the condition register that lets the program counter change. But those are the flavors of our instructions. They generate a sequence of button presses causing information to flow through the data paths of the register machine. And what we can do now is put these pieces together to start building more interesting kinds of register machines. So let's go back to our little example of incrementing a sum. There's the data path we had before, and we can start to describe the sequence of operations. In fact, if you go back to that slide, you'll see we can do it very directly. First, we open up the X button. That moves the constant 0 into the sum register. And our description for that, in terms of our instructions, says assign into the sum register the output of the constant 0. Notice this implicitly also defines the data path, that I need to have that connection. The next instruction then says open up Y. That is, assign into the sum register what I get by letting the things from sum and the constant 1 flow through the operation of plus and back in through that button Y into sum. Notice again, this implicitly defines what needs to be connected and controls the sequence now of moving a value into sum. And then we saw to get the constant 2 in there, we needed to open up Y again, letting another value flow through. And there's the sequence of operations we need. But of course, we don't want to have to keep writing a new line for every increment we'd like to do here. We'd really like to write a little loop that says, keep opening up Y until you get to the right point. So how could we adjust this to allow for the sequencer to keep opening up Y, moving a new value into sum, and incrementing sum as many times as we'd like? Well, here's the simplest kind of branch that we can have in our sequence of instructions, called an unconditional branch. Notice the change we make in the little controller. We still have our assign of sum to the constant 0, our starting point. But then we put in a label, called increment in this case, but a marker that keeps track of where we are. We're not actually going to give a line number to that. We'll only put a number on the lines that involve some actual movement of things in the data diagram. But immediately below that, we have that assignment of sum to be a new operation. And whereas before we would have done an additional call or additional instruction for assigning sum, we're going to put in a special instruction called a goto. And that goto says, go to the label increment. In terms of the little sequence of instructions, it's basically saying jump back to that label and keep following through the instructions starting at that point. In terms of what happens inside of our sequencer, think of it as follows. We have some value sitting in the program counter. And initially we're going to add 1 to that and put that into a temporary register called the next PC, or the next program counter value. We'll then go off and activate the instruction at the point that program counter indicates, the line number that is indicated by what's currently in PC. Typically that will be the next instruction. Activating that instruction will usually just cause some button to be opened and some values to flow through the data path, so that then we can update the program counter with what we stored away in next PC. And that will typically therefore point to the next value or the next instruction, and we'll keep walking through this sequence. We'll just keep doing this. Notice, however, that if the instruction pointed to by the program counter is one of these gotos, that will actually directly write a different value into next PC. The value corresponding to where increment is, which is the value 1, if you like, the next line, will get installed into PC when we evaluate line 2. And this will cause the sequencer to jump to a different point in the instructions other than the next instruction, and therefore pick up the computation at that point. In fact, let's look at this little system to see what happens. We start off with the program counter at 0. And therefore the sequencer sets next PC to 1 temporarily and evaluates the instruction at PC. That basically says open up button X, assign the constant 0 into sum. Having done that, we put that temporary next PC value into the program counter and go back around. The sequencer then sets up a new value into next PC, puts a 2 in there, and then it evaluates the instruction at line 1, which basically opens up button Y, moving the value in sum and the constant 1 through the plus and around, and into sum again, therefore putting a 1 into sum. Having done that, this value in next PC is restored to PC, namely a 2, and we go back around. At this stage, the sequencer puts a 3 temporarily into next PC and operates or activates the instruction at 2, where the program counter is pointing to. But in this case, this is a goto, and what that does is it rewrites into next PC the line number or the pointer location corresponding to the label increment, namely a 1. So it changes next PC. Notice, nothing to press here. There's no instruction that causes a button to be pressed. So we now put what's in next PC into PC and go back around. Aha! That means we've put a 1 into PC. We set up next PC to be a 2 temporarily, and we evaluate the instruction at 1. We've just looped. Therefore, we open the button Y, a new value flows into sum, and we go and put next PC into the PC, putting a 2 there, and start again. Oh, and this is just like before. We now put a 3 temporarily into next PC, evaluate the instruction at 2. That says, oh, change next PC to have the label 1 corresponding to the increment there, and go around. So in fact, we now have an unconditional branch. We're going to loop forever, adding a 1 to the value in sum and constantly incrementing it. But we see that in fact, by changing what the sequencer looks at, we can jump to places in the sequence of instructions. Of course, unconditional branches, while useful, aren't always what we want. They're going to create an infinite loop in which we keep, for example, in that little sum case, adding 1 into what's in sum and doing so until we overflow the register. What we need as a way of deciding when we want a branch or not. So let's go back to our GCD case and think about what we might like. Remember in GCD we saw that we wanted to open up a sequence of buttons in a particular order. First moving a value into T, then moving B into A, then moving what was in T up into B, but repeating that process. And so in fact we could create a little loop using one of these unconditional branches, stick a label in, and have a goto that takes us back around and runs through this sequence of operations. The problem is we'll keep doing that ad infinitum. We'd like to know when to stop and just return the value that we have in A. So we need a way of testing. To do that, we not only add a test box to our system, but we set up a particular condition for the sequencer. Remember that a test operation will do whatever the appropriate piece of circuitry is, and then output a single bit that goes into what's called the condition register. This bit, in essence, corresponds to true or false. Thus, in my example here, the first line under the label test B is a test operation that says use the wire connecting the output of equal, given the appropriate inputs, and put that directly into the condition register. Set up a point there. Remember that the sequencer automatically goes on to the next instruction. So having done this test operation and setting a bit in the condition register, the sequencer will take us to the next instruction. And there we have what's called a branch instruction. The branch instruction, when executed by the sequencer, in essence does the following. It says, check the condition bit. If the condition bit is true, then overwrite what's in the PC counter. Take that label, GC done, wherever it points to, and slam that into next PC. In that case, it will cause the sequencer to jump to that point. On the other hand, if the condition bit is false, we won't do anything, which means the next PC will automatically drop down to the next instruction. So now we have a conditional branch in which we test the value of something, and when, based on what that value is, either continue on with the sequence of instructions immediately after the next one, or jump to a particular point. Here then are the details again of a conditional branch. We have an instruction in our sequencer of the form test. This basically says push the button which loads the condition register from this operation's output. Notice again that this description also describes what wires need to be connected. The operation equal must have a wire from register B and a wire from the constant 0 into it. And test causes the output of that operation equal to set a bit into the condition register. Associated with that test instruction will be a branch instruction, the instruction immediately below it in almost all cases. The branch instruction has as its piece a label that says where to jump to if I want to have things happen. Again, this should be some label that's simply put into the code somewhere. The effect of a branch instruction is to overwrite the next PC register with that value, that point in the sequence of instructions, if the condition register is true. This means if the condition register is true, one cycle later we're going to jump to that point. On the other hand, if the condition register is false, nothing is done. Branch simply is skipped, and that means the sequencer will go automatically to the next instruction in the sequence. So we've now seen how to design register machines to compute what are basically iterative operations, GCD being one great example, sum being another one. Notice we've pointed out, though, that the instruction sequences we generate here always contain implicitly information about what the data paths are. And in fact, just given the instruction sequence, we could always draw out what the data flow diagrams look like. So as a consequence, we can just skip the data paths when describing a register machine. We simply need to think about what registers do we want, what operations do we want, and what sequence of instructions do we need to do to move information around. That'll make life a little easier for us as we design bigger register machines. Notice as well that every operation we've used so far in our register machines has been fairly abstract. By abstract, we mean we've assumed that we can buy a little circuit that computes things like equal, or remainder, or sum, or minus, or any other such operation. And at some level that's okay, but here abstraction really means that there are a set of multiple lower level operations that will implement that particular idea. Now some of those lower level operations are going to involve basic hardware, AND gates and OR gates, the kinds of things you'll deal with in 6002 and 6004. And for our purposes, it's convenient to assume that we do have a basic set of primitive pieces of circuitry that we're just going to rely on. Some of those lower level operations, however, might themselves be just sequences of register machine instructions. Well, it's reasonable to assume that I could go out and buy an equal tester or a plus operation. What about remainder? Well, in fact, we probably want to be able to build those things just out of manipulation of much simpler register machine instructions. So now let's go back in and see how we can replace this single instruction, assuming we have a remainder box, with a sequence of instructions that actually builds remainder directly out of much simpler operations. So here's our sequence of instructions for GCD. The only change we've made is where before we would have had an assign statement that ran directly through a remainder box, we've set up a little loop. And notice what that loop does. The loop moves the contents of register A into a temporary register T, which says we're going to have a new register use there. And then what do? We check to see if T is less than B, or rather the contents of register T are less than the contents of register B. If they are, our sequencer will jump straight down to the label rem done, and we're set. We've computed the remainder, and we can carry on as before. If it's not, then we'll subtract what's in B from T, put that into T, and go back around through the loop, checking again to see if we have something. So basically, we're computing remainder by successively subtracting B units off of what's in T until we get something that's small enough that we can actually do the work we want to do. This means we've replaced that single assign instruction with a loop that does the computation for us directly. Notice that now our sequence of instructions has two loops in it. It has the bigger loop between GC done and test B that goes through the computation to get the next stage in GCD, and it has an inner loop between rem loop and rem done that does the actual computation for remainder. We're going to come back to this idea of that inner loop next time around. In fact, we want to take that idea and use it. What is that idea? The idea that I could, in principle, write a set of very primitive register machine instructions to compute something like remainder or some other operation. But I'd like to know that having done that, I can extract that away. And why do I want to abstract it? Well, because we're going to talk about building an evaluator, a CPU. Clearly a very complicated device. And we're really only interested in the core of the CPU, eval and apply. So we're going to use abstract register machine operations for all of the other instruction sequences and circuits. Things like self-evaluating we'll assume is just simply some operation. It's not any different than what I did before. I'm treating plus or less than as abstract. Self-evaluating is going to do a similar thing. There's no particular magic there. If I needed to, I could build it out of a sequence of register operations. But for simplicity, as we get around to building our CPU, we're just going to assume that there's a box available to do that for us.